Dealing with climate change is one of the biggest challenges to be faced by our current political and economic systems. Knowing where, how fast, and how much the climate is changing is essential information both for mitigating the effects of climate change and for adapting to changes in climate that we expect are coming but have not yet occurred. While satellite-based instruments provide measurements that can be used to detect changes in climate, they require calibration and validation to ensure that they're providing an accurate picture of the evolving state of the atmosphere. Ground-based measurements of the state of the atmosphere, such as temperature, pressure, and humidity, between the surface and the top of the stratosphere at around 50 kilometers, provide high-quality measurements to validate measurements from space and complement satellite-based measurements by sampling key atmospheric regions. High-quality ground-based measurements of climate variables from sites around the world provide the observational backbone for climate science and the data needed to better understand key atmospheric processes which affect weather and climate. Better understanding of processes improves the quality of computer models of the atmosphere, leading to better weather forecasts and better simulations of current and expected changes in climate. When high-quality vertical profile measurements of essential climate variables are available over many years, they can be used to detect changes in climate. But only if the measurements contain no artificial offsets or drifts over decades of operation. Previous analyses of global temperature trends showed large discrepancies between trends derived from space-based instruments, balloon-borne instruments, and expected trends diagnosed with state-of-the-art models. Much of the source of uncertainty in trends in upper-air climate data records result from frequent and often undocumented changes in instrumentation. Often, little attention is paid to ensuring the long-term homogeneity of the measurement record when changing from one instrument to the next. This is because historical observations were made primarily to be used in weather forecasting and not to detect long-term changes in the climate. The result was measurement series that fell far short of the standard required to reliably detect changes in climate and thereby acted as an impediment to understanding climate change and its causes. Even after attempts to improve the quality of measurement series by applying methods to remove apparent discontinuities, many measurement series fail to meet the needs of climate scientists. A new measurement network has been established as part of the Global Climate Observing System, also known as GCOS, to overcome historical problems related to climate data record discontinuities and to provide the highest possible quality measurements of essential climate variables in the atmosphere. This new network is known as GRUAN, the GCOS Reference Upper-Air Network. GRUAN is an international ground-based reference observing network designed to fill an important gap in the current global observing system. GRUAN reports directly to the GCOS Atmospheric Observation Panel for Climate and is advised by 4 of the commissions of the World Meteorological Organization. GRUAN is envisaged as a global network of eventually 30 to 40 sites. New sites are continually being incorporated into the network. GRUAN differs from many other measurement networks as its focus is on making reference observations. A GRUAN reference observation is traceable to an SI unit or an internationally accepted standard. Includes a robust, traceable estimate of measurement uncertainty, is documented in accessible, peer-reviewed scientific literature, is validated through comparisons with complementary ground-based measurements, and includes a complete metadata description. Comparisons with measurements from complementary systems are used to evaluate the quality of the observations. Such comparisons between multiple systems are also essential for managing changes in instrumentation. Furthermore, measurements from GRUAN sites are well suited to assess the quality of environmental satellite observations from various operational and research satellites orbiting the Earth. Environmental satellites operated by various international space agencies provide global coverage at different times of the day, using similar but not identical suites of atmospheric sensors as used at GRUAN sites. Intercomparing satellite data against sets of co-located GRUAN observations has become an important component of monitoring and validating the observations from different satellites. The compilation and stewardship of long-term datasets that are comprised of co-located GRUAN and satellite observations are key to GRUAN's and International Space Agency's coordination activities. The intercomparison of co-located observations, as well as laboratory studies and field intercomparisons, are used to minimize the impact of systematic biases on long-term observations and are essential to establishing reference quality measurement time series. The GRUAN measurement strategy aims to make high-quality measurements from Earth's surface to the top of the stratosphere over several decades to accurately quantify trends. GRUAN will provide data to validate measurements from observing systems that are more spatially extensive, such as satellite systems and the global radiosonde network, leading to improved global climate records. GRUAN will measure climate variables using a number of different but complementary techniques to validate derived measurement uncertainties. An important goal is to characterize observational biases and estimate measurement uncertainties. Extended metadata and comprehensive documentation of the observing technique will describe the measurements being made by GRUAN. Long-term stability of measurement series will be ensured by managing instrument changes. This in turn will improve the overall performance of the upper-air observing network. Measurements will be tied to SI units or internationally accepted standards through a fully documented traceability chain involving specific calibration procedures and uncertainty evaluation. Increased concentrations of carbon dioxide in the atmosphere affect atmospheric temperatures in a very specific way, since in general carbon dioxide warms the troposphere but cools the stratosphere. Diagnosing the vertical structure of atmospheric temperature trends is therefore an important part of the evaluation of the role of carbon dioxide in climate change. Historical records of upper air temperatures are insufficient to meet the growing range of needs for studying climate. This is because they lack continuity, homogeneity, and representativeness of data, primarily because past measurements were seldom intended for climate research, but mainly for short-term weather forecasting. A way of separating climate change signals from the inevitable non-climatic effects caused by measurement biases, instrument instabilities, and network inhomogeneities is essential. GRUAN operating protocols for upper air measurements of temperature ensure that any changes in measurement methodology are managed to ensure that no discontinuities are introduced into GRUAN measurements over the long term. Another focus for GRUAN is to better quantify trends in atmospheric water vapour, which is also a greenhouse gas. Atmospheric water vapour concentrations are determined in large part by atmospheric temperatures. Warmer air can hold more water vapour. As a result, water vapour acts to amplify the climate warming induced by other gases such as carbon dioxide. There is some uncertainty regarding where and how water vapour concentrations in the stratosphere have changed and whether any future changes are expected to influence Earth's energy budget. Because there are just a few parts per million of water vapour in the stratosphere, making measurements of its concentrations is notoriously difficult. The result is that records of water vapour, particularly around the tropopause, tend to have large uncertainties. Incomplete understanding of the key mechanisms controlling water vapour in the tropopause region leads to deficiencies in the predictive skill of global climate models. The main sources of water vapour measurements around the tropopause are from space and aircraft-based instruments, as well as balloon-borne instruments being flown at GRUAN sites. Since 2005, GRUAN has reached some important milestones. A GRUAN lead centre has been established at the German Weather Service at the Meteorological Observatory in Lindenberg. A robust process for evaluating and certifying measurement programs at candidate GRUAN sites has been established. 7 sites have had their RS-92 radiosonde measurement programs certified in this way. A network expansion workshop held in June 2012 defined approaches to be used to guide the expansion of the network. Implementation plans have been developed and revised to ensure that GRUAN evolves in a way that is consistent with meeting the needs of its users. 5 task teams have been established to progress the development of different data products, to coordinate activities across sites within the network, and to ensure that GRUAN measurement regimens are founded on the best possible science. A formal manual and a guide documenting GRUAN operating procedures have been written. The guide formalises the GRUAN site assessment and certification process. The first GRUAN data product, the RS92 radiosonde product, is being disseminated to users through the NOAA National Centres for Environmental Information. These data are being used by the climate research community, and several peer-reviewed publications have already used these data. Momentum is building across GRUAN, and new sites continue to join the network, especially in the mid-latitudes of the Northern Hemisphere. Sites in the tropical belt and in Africa and South America are still lacking, and there is an urgent need to recruit new GRUAN sites in these regions. GRUAN is already providing data streams that are meeting the needs of its core user groups, and additional data streams currently in development are expected to become available in the next year or two. These include LiDAR, microwave radiometer, Fourier transform spectrometer, and ozone sonde data products. If you have an interest in GRUAN or are willing to contribute to GRUAN, please contact the GRUAN Lead Centre.